Imagine you want to rotate something. Normally it's not a problem. If you have a suitable motor, you can attach whatever you need to rotate to the motor's shaft and power it up. Now imagine you have a wall here. You can't drill through it because the contents on the right are under pressure, and you can't put the motor inside because it will become unserviceable. Magnetic coupling can save you day in this situation. I tried out a couple of designs and did some experimentation, so stay tuned and watch till the end. We all know how magnets work in practical terms. They attract metal and attract or repel each other. All magnets have two poles. We usually call them north and south, and different poles attract and same poles repel each other. If I put a thin enough wall between a couple of magnets, by moving one I can move the other one without touching it. Although if I rotate the first, the second won't move, but I can move the magnet in circles and the second one will repeat the trajectory of the first. I have a set of 10 by 3 mm magnets. They attract each other at a force of around 600 grams or 1.3 pounds. Let's try building some coupling with them. I printed two identical flanges. Let's put a magnet inside both of them. For this experiment I don't really care which pole is south or north. I take a stack and decide that this side is going to be different from the other one by the fact that I drew a dot on it. Then two dotted or two undotted sides will repel each other and the dotted plus undotted will attract each other. After assembling our coupling, we can see that our flanges are touching each other and we want to have some space, so I'm going to put a 4 mm spacer between them. Let's see how much torque this coupling can handle. I'm going to connect one flange to a kitchen scale and the other one to a handle, so I can rotate them relative to each other. The probe that touches the scale is exactly 100 mm apart from the middle of the axle, so we'll get the same amount of Newton meters as we're getting kilos on the scale. First experiment. One magnet in each flange at 4 mm distance. We are getting 15 grams. Not much, but even one asymmetrically placed magnet can transmit some torque. Let's draw this to better understand how this works. When there is no force, magnets are aligned and attract each other alongside the axle. You can see that there is no lateral component. But as soon as we start spinning one of the flanges, an offset is introduced and the attraction force is no longer parallel to the axle. We can draw a triangle here and the lateral component becomes apparent. This lateral force will try to rotate the secondary flange in sync with the primary one. Let's add one more magnet to each flange. What do you think will happen? Is it going to double the torque? Second experiment. Two magnets in each flange at 4 mm distance. We're getting 23 grams. It did not double our previous result, but we're definitely getting a better coupling. One interesting property of magnets is that their force doesn't change linearly relative to the distance between them. The magnetic force follows the inverse cube rule. If you increase the distance 2 times, the force will decrease 2 times cubed, meaning 8 times weaker force. If you increase the distance 3 times, the force will decrease 3 times cubed, meaning 27 times weaker force. Also, I think I broke a magnet. So yeah, these are quite fragile, so be careful. Remember our diagram? Let's try to understand how the attraction force changes with increasing offset and rapidly dropping magnetic force over longer distances. Here is an approximate graph of the attraction force of the two magnets. On the horizontal axis we have an offset in units of the gap between the magnets, where 1 means an offset of 1 distance between the magnets, 2 means 2 distances, and so on. On the vertical axis we have the percentage of the force that the two magnets attract each other with at a single distance with no offset. You can see that at first the lateral component grows way faster than the magnetic force weakens. But at some point the force is going to peak, and if you introduce more torque at this point, the force will start dropping fast and the coupling will slip. Let's add more magnets. Third experiment. 4 magnets in each flange at 4 mm distance. We're getting 46 grams, pretty much doubling the previous result. We can try adding more magnets, but if I draw this, you'll probably notice that the more magnets we add and less lateral separation they have, the smaller the offset will be when all the lateral forces are already cancelled out. So simply adding more magnets likely won't scale that good. But I have something better in mind. Let's alternate the polarity of our magnets. Our diagram will then look like this. You can pause the video and make a prediction in the comments. How much do you think the maximum torque will increase? Fourth experiment. 4 magnets in each flange at 4 mm alternating. We are getting 69 grams. Not bad, but I personally thought we will get at least double of our previous record. I think one of the reasons why we might not be getting a higher value is because in this setup at some offset the two flanges start repelling each other, so you need to contain the expansion, otherwise you might lose some effectiveness due to increasing gap between the magnets. Let's add more spacers and see if this has any effect. This stand is not very rigid, but it might just give us a hint if our hypothesis has some truth to it. Fifth experiment, 4 magnets in each flange at 4 mm alternating with no axial wiggle room. We are getting 77 grams. Not bad at all, so now we are almost at a double relative to our monopolar setup. There is also another thing I'd like to try. In theory, reducing the gap from 4 to 2 mm should make the attraction 8 times stronger. Will we get 8 times more torque at 2 mm? Also, increasing the gap from 4 to 6 mm should decrease the torque by more than 3 times. Sixth experiment, 4 magnets in each flange at 2 mm and 6 mm alternating with no axial wiggle room. 2 mm resulted in 112 grams, which is 1.45 increase. Almost seems like a root 2. 6 mm resulted in 46 grams, which is 1.67 decrease. Seems like we are not getting even a linear correlation, not to say a cubic one. I'm not sure I know how to explain this, so if you have any ideas why, share them in the comments. Also, consider subscribing. This setup, by the way, is not the only one possible. The second option is to go coaxial and rotate magnets 90 degrees. Let's test this setup as well. The gap between the magnets is the same 4 mm, so in theory this should perform more or less the same as our flanges did. Seventh experiment, 4 alternating radial magnets. We are getting around 105 grams. Let me remind you that the 4 mm alternating magnets on the flanges yielded around 77 grams. That's a solid third more of a maximum torque. I don't think this means that the coaxial couplings are inherently more effective. The reason I believe is purely geometrical. These magnets are quite wide relative to the coupling diameter. The center of the magnet is recessed relative to the edges, so when rotated, the edges come closer than the initial gap of 4 mm to the opposing magnet, likely increasing the force. That's it for today's video. I hope you found magnetic couplings as fascinating and useful as I do, and maybe you have a use case or two for them as well. If you want more content like this on this channel, don't forget to subscribe. And those who watched this video are probably going to guess where this one is going. See you next time.